Hello everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on curve fitting, and we're going to be talking about polynomial regression. Now, if you remember from your previous lesson, we did linear regression, and if I recap briefly, if you have a set of data points that have a linear trend to them, you would fit a linear regression, and we have introduced a reduction of the sum of the square of the residuals, and basically the model we're trying to fit is a0 plus a1 xi, and we took the derivative of this in terms of a0, a1, then we got these two equations, and then we got these final two expressions of a1 and a0, which basically we're solving for the slope and intercept that would best fit these set of data points. So what if you actually have a set of data points that have certain curvature to them that would actually be described better by a higher order polynomial, a second order and above? What would you do? Well, we're going to be presenting the theory behind fitting a second order polynomial and also higher order polynomials as we're going to be developing the code. And it follows the same technique as we did with the linear regression. What do I mean by that? We are still reducing the sum of the square of the residuals. And if you remember, the residual is the distance between those measured values and also this line in the middle here. So basically the model that you're trying to fit. So if you can minimize the distance between the points and the model, now you have found the best fit for these particular data points. So what is the model that we're trying to fit here if it's a second order polynomial? Well, it's going to be a0 plus a1 xi plus a2 xi squared. So in this case, instead of just finding a0 and a1 when we're dealt with linear regression, now we're finding a0, a1, and a2. And much like what we did with linear regression, we're going to take basically the partial in terms of each one of these three, and we're going to place it equal to 0 because again this is an optimization problem. We're trying to find the critical points, or basically where these are where the error is the lowest at a0, a1, and a2. Now, this is still, much like with linear regression, this is still a chain rule when we're differentiating it. So the outside is just going to be 2 multiplied by this for all of them. And you're going to find here, when we take the derivative in terms of a0 for the inside, you're going to find we have -1, so you can have, say, -1 here, and we take the derivative in terms of a1, we're left with xi, or negative xi, so you have negative xi here, and we take the derivative in terms of a2, and we have negative xi squared, and we have negative xi squared here. So what we're going to do is we're going to distribute the sum, and we're going to multiply the xi here and xi squared of inside here, and we're going to be presented with this type of 3 equations, and we're going to be reorganizing them, that the first terms here are a0, second and a1, and the third at a2, because as you see in front of you here, we have actually created a system of 3 equations, right? The system of 3 equations where each one of the equations has 3 unknowns, a0, a1, and a2. So let's look at the first equation. So the first equation, the coefficients of a0 is n, which is the number of data points. In this case, we have 20. And this is the sum of all the x values, sum of xi squared. And here we have second equation, here the sum of xi, which is basically the same here. And I want you to see a pattern. You see that diagonal? So here this is the sum of xi, here the sum of xi, here's the sum of xi squared. This also has the sum of xi squared. This has the sum of xi squared. This here, the coefficient of a2 in the second equation, sum of xi cubed, and also down here we have the sum of xi cubed down here as well, and we only have 1 for xi to the 4th. So if you look at the b vector, or the right side, we have the sum of yi, this is sum of yi xi, and this is the sum of yi xi squared. So if we can use basically the numbers that we have here, which is basically the data points that we're trying to fit, and we can create the augmented coefficient matrix A on the left side, and also the values on the right side, and now we have a system that we can use Gauss elimination, for example, or any type Gauss elimination, Gauss Jordan, or LU decomposition to actually solve for the unknowns A0, A1, and A2. And this is basically the code that we're going to be creating for the in the next lesson. Now, I do want to mention something. This example shows how you can fit a second order polynomial, but a third order polynomial is not that much different, because when you are creating the matrix for say a third order polynomial, here the only thing that's going to be different is that we have a3 now and xi to the third, and there's going to be another derivative in terms of a3, and we're going to have a fourth here we're going to have a fourth equation. So we're going to have four unknowns, a0, a1, a2, and a3, and now we're fitting a cubic. And you can do this for a fourth order polynomial and a fifth, and so on. Now, the code that we're going to be creating is going to be a general code. You're going to decide what type of order you want to run. Do you want to fit a second order polynomial and, for instance, see the r squared? So let's assume we fit a second order polynomial and we have an r squared of, say, 80 or 0.8. So it captures 80% of the essence of the points. Then you were like, okay, so I'm gonna see what a third order polynomial would do, what a cubic polynomial would do. And you apply this and you find that, well, it gave you an 80% or 85% r squared, so it's definitely an improvement. And then you run a fourth order polynomial and maybe now captures 90%, and maybe at this point you do a fifth and maybe it decreases, or maybe it increases slightly, or it doesn't change. But now you might have narrowed down on what type of model best captures the essence of the data points that you have collected. So in the next lesson, of course, we're going to be developing this generalized code. So that's it for this lesson, and I will see you in the next lecture. Thank you very much.